Cambridge Muslim College, training the next generation of Muslim thinkers.
Assalamu alaikum, everybody. What I'm going to talk about, inshallah, is obviously the title is Science and the Inquiry for Truth, but it's actually going to be a much broader presentation than that, because what I hope to do is to convey something to you about aspects of science that to your eyes will have remained almost veiled. It sounds like a bold thing, but in fact there's a lot of science that remains undercover because the public, for some reason, it's not popular with scientists, and the media present a very different picture to the reality. So this is the reason I'm here. But one aspect of the science I want to present is in relation to how very fundamental sciences have revealed what is the nature of mankind. Now, this is sounding even more mysterious to you, I guess. But what I'm really talking about is we as Muslims already believe. We are not just a physical person, we have a soul. We are a spiritual being as well as a physical being. So this is something mysterious previously to science, but I'm hoping to show you that this is something that's actually creeping into science in a very large way in some senses, which I'll hopefully, inshallah, explain. How many of you here are doctors or medical doctors? Okay, excellent. So I won't be going into too much technical detail, so bear in mind this is aimed at a lot of people in the general public. And what about people who are scientists here? Okay, excellent. You're a scientist? Okay. All right. How many of you, you're physicists, I've met you before, and you're a mathematician? Okay. So what type of mathematician are you? Pure maths. Pure maths, okay. Hopefully that's good. So what I'm going to do will, to some extent, sometimes sound a little bit basic to you, but and for others, I don't want to blind them with too much science. So we're trying to keep it fairly halfway between. So whilst at medical school, I asked a very important question, and some of the doctors here may want to think about it themselves. Is that if I was to lift my hand up and reach for a cup of tea, where is that intention coming from? Where's the signal coming from? Is it from my brain? So we all come across the brain as a picture of this blob of fat with lots of lines in it. But where is the signal coming from for me to reach up to pick up a cup of tea? And the answer I got from other colleagues, medical students, was it's just stimulus response. So I thought about this and I realized that obviously stimulus response doesn't really help me at all, because there are lots of things that have stimulus response. I can program a little robot to avoid hitting the walls and do all sorts of things which purely don't involve any conscious awareness. But why did I raise my hand up to reach for a cup of tea? That's the start point. So the mystery is, what is stimulating the brain in order for me to be aware of what I'm doing? Why am I actually intending anything? So this is the start point. So how do we get from here all the way through a long tour through physics and ending up at all sorts of things relating to, hopefully, each other's soul? But I'll come on to that slowly. So first of all, there is a lot of science that actually gives a picture of that correlates with our religious view. And there are actually very many aspects of the Quranic revelations and other monotheistic revelations that actually coincide with science. So I'm going to just start with a few motivational things. So I'll start, first of all, with the next slide, which is, first of all, what is science? Just try and come up with some sort of definition, because we all talk of science as some sort of solid rock or perfectly it's understood object, but it's obviously not as clearly understood as that, and it's very difficult to define it. And science is, in fact, you could describe it as a systematic enterprise, and that builds up and organizes knowledge in a form that is testable, by which we come up with explanations and predictions about the universe. That's one definition. There are many definitions, and many of them don't encompass all of these factors. The important thing is that we have some sort of explanation that's testable and that we can make predictions with it. And it should involve predictions about the world around us. So the next thing is, as we're talking about science and truth, what is truth? An even more difficult thing to define, because as you'll see shortly, there's a lot of equivalent statements or tautologies about science. So here we have a question. What is truth? There's one particular definition could be that it's a property of being in accord with fact or reality. Then you're going to ask me, what's fact or reality? So then what's fact? Fact is a thing that is known or proved to be true. Well, there's a tautology. We're already using the same terms that we started in the definition of what we tried to explain. And then what is reality? It is the state of things as they actually exist, as opposed to an idealistic notion or an idea of them. So you can see it's a very difficult area to understand, a difficult thing to achieve, to understand how we reached what we understand as truth. And try to give you an idea of the confusion behind science and how we determine what is actually factually correct and what's not factually correct. So what is religion? And there are so many definitions you'll find in religion in the dictionaries. And one of the most useful ones I found was this simple looking definition, but it's a set of beliefs concerning the cause, nature and purpose of the universe, and especially when considered as the creation of a superhuman agency, usually involving devotional and ritual observances, often containing a moral code governing the conduct of human affairs. Okay, so what I'm saying is that we often talk about this area of the second half, but we very rarely talk of the first half. And it's the first half that actually overlaps with science. So, jumping straight onto the things that I mentioned were motivational, here's a line from, from Surah Baqarah. I'll concentrate on the second line here. And it says, and do not speak of those who are slain in Allah's way as dead. Nay, they are alive, but you do not perceive. Of course, how can you make sense of such a sentence in a scientific setting? Clearly, from a scientific point of view, this sounds like nonsense. But of course, we know from an Islamic point of view that we believe that fundamentally to be true. That this is a line that's true. Okay, you may consider it relating to martyrs, etc. But we don't doubt the Quran. So look at this puzzle, and to leave this puzzle with you, just another bit of motivation, and this really sort of puts things into perspective. I'm going to ask you to all imagine that you take your brain out, leave it in your room at home, and then wander around the rest of the day without your brain, but somehow you connected to your brain, you can still think that you can still act and behave as normally as you do now, but your brain is not inside your head, but sitting somewhere else. The question I'm going to ask you is, where are you? Sorry? Okay. So the question that I want you to reflect on is that. Okay, so a brief discussion then now about science and truth. So we've become so used to science as being such an effective discipline that advances in science are so commonplace, using mobile phones, telephones, watching television, that we become so trusting of it, we're actually using it to judge truth. And this is the problem with science, that actually using it as some sort of litmus test as a judge of truth. So how reliable is science as a judge of truth? Well, I know that certainly if I test a plug socket, if it's 240 volts, I can safely plug in a device. But can I really use science to judge whether or not something is beautiful, or if a Chinese meal tastes better than a Thai meal? Can I use it for that? And the answer is, of course, not. So how reliable is science as a judge of truth? For instance, some people think that theory of everything is literally the theory of everything, but of course, physicists would know the theory of everything refers to just forces and matter. There is really no theory of everything. So you may say, what about evolution? Well, evolution, does that explain everything? Well, for instance, does it explain the origin of life? Or does it explain, can we use this to apply it to cosmology? Do universes evolve, like Dawkins and various other people think they can apply it to other things? Of course, none of these things are true. Neither explains the origin of life, and nor does it explain, nor can it be used to explain anything other than biological systems and how species develop. So it's not really a theory that encompasses all facts. So the next thing is then, in fact, if I was to consider where we are today, I want to give you this little picture of what I think scientists really are doing today. This is a caveman, and I went to a lecture by Roger Penrose who used it for a slightly different purpose, which was he was trying to ask whether or not this mathematical knowledge this caveman had acquired was going to be any survival advantage. But here, I'm going to ask you to reflect on this in a slightly different way. Are we any further than this caveman? Well, the answer is probably we're in a similar position, just a bit further along technologically. We still have a lot of ideas, and we can't confirm if they're true. We don't have the technology to confirm it. And we're still developing new science fiction-y sort of mathematical ideas. So we're really sort of where we were in this particular picture. Okay. So I'm going to ask now to move on to a little bit more structurally what is how we classify sciences. And just to give you an idea, we all think of sciences as being, complete objects, all fully understood and tested, but they're clearly not. And I just want to break down science into three sections, which is theories, hypotheses, and conjectures. Now, first of all, a theory is a very complete set of ideas, which has been accepted by a large number of scientists, for which which is ample experimental evidence, and which is a very reliable prediction of future outcomes. So theories, I'm given a list of some theories. These are ideas in physics. For instance, we understand gravity very well. General relativity explains a lot about the structure of the cosmos. But what about things like string theory? We call it a theory, but it's actually not a theory, really, in that sense, because we have absolutely no experimental evidence at all. And it's still an idea, like with other things, like supersymmetries and theories of everything. So they're not really theories. They're just ideas which are compelling and interesting, and they may turn out to be a theory, but they're not theories. And likewise, the idea of multiverses, I'm not going to go into this. They're a very diverse bunch of objects, but we talk of multiverses as if they really exist. Maybe they do, but we don't know. And at this stage, there's actually no way of testing them at all. So these are just conjectures. So really, the true classification of science should be theory, hypothesis, and conjecture. So, but that's not the way the public have been presented the information. Pardon me, let's flap this. The whole point is that a conjecture or a hypothesis can be proved to be untrue, and so we're subject to the fashion led by the media that somehow a hypothesis or an idea or a conjecture is actually a fact and a true theory, but it's often not. So I'm going to move a little bit further, a little bit deeper into science, and I'm going to go to the language of science. This is mathematics. Now, I'm talking about this as a language of science because although in biology we use it possibly less so, in most physical sciences, it is actually the backbone of it, and in fact the only way to express ideas. In fact, we don't use, in physics, for instance, really much English. And in mathematics, obviously, mathematics being the backbone of the actual entire theory and the mathematical ideas behind it. So I'm going to tell you a brief story about the difference between mathematics and science, and why I'm going to tell you this is very important. But to give you an idea of its importance, we're going to look at this picture here. This is a view from a train, and an engineer and a physicist and mathematician were travelling by train to New Zealand, and they saw a black sheep from the window. And the engineer explained, look at the sheep, look, the sheep in New Zealand are black. But the physicist objected, you can't claim that. Well, if you see another sheep, maybe a couple of sheep, maybe we can say all sheep in New Zealand are black. But the mathematician smirked and said, all you can say is that of the sheep in New Zealand that we can see from this train, their sides facing this train are black. And of course, he could have been right. So this, although amusing, is actually a very clear illustration of how mathematics differs in precision to science. And I'm going to point out to you something really very, very fundamental, which is this. A theorem. There's just drop the Y, change it to an M, and you get something called a theorem. Now, this is different from a theory, and you would have it believed that somehow theorems in mathematics would just go out of date and then they gather dust and get filed. But no, it's not true. A theorem in mathematics is quite different from a theory in science, in that it's always true. That sounds strange, but it's a fact that's of eternal truth, because it's just a set of ideas that could be proved to be rationally correct based upon a set of assumptions. So in mathematics it's very different. So we've all heard of Pythagoras, and clearly he's being advised here by one of his close friends that he should have patented his idea because it's used everywhere. And the reason for that is because it's never out of date. So this is a theorem. So what about an idea that is in physics or in science that has theorems in it, things that are always true, things that are factually, eternally true, in the sense that we human beings can call anything eternally true? Is there such a thing? So I will come on to that, and I'm going to move very swiftly because there's a lot to cover, but I'm going to try and give you an idea of quantum theory, and I'll explain the reason why it's important, of course, because it is the theory of the physical world at a fundamental level. It's not some abstract thing out there that somebody in a science department reads about. It's actually the language of your mobile phone. Okay, so it's the language used by day-to-day electronics and day-to-day laboratory usage. So here we have a very, very simple picture of an atom as a reminder, just to put you into the picture as to, in case you've forgotten, and I'm not expecting anyone to know much any more than this, and I'm trying to keep everything as untechnical as possible. But here we have an atom. We remember it's got a bit in the middle called a nucleus, and it's got a proton which is positively charged, and a neutron which is neutral, and then there's an electron that spins around, and it's negatively charged. You don't really need to even know any more than that. In fact, the reason I put this up is I'm going to use the word particle a lot. Okay? By particle, I mean any small, or very, very small object. It could be just one of these bits. It could be the electron, or it could be just the proton. But you can also consider the whole atom as a particle, because it won't fall apart unless you try and bust it with something. It's going to stay together. And so it's one tiny little unit at a very microscopic scale. So that's what I mean by particle. So I'm going to now move on to the next stage, which is to show you as simply as possible, what the mystery of quantum mechanics really is and why it's important. And I'm going to relate it to something that should be familiar, which is like a ball which you kick around or a tennis ball which you fire about. And I'm going to give you this famous experiment. Now, it's worth spending a few minutes on this because this captures the entire mystery. Though it sounds crazy, but it's actually true, you could, if you reflected on this experiment enough, capture the entire mystery of quantum mechanics. So it's why it's worth having a look at. Here's a wall on the left-hand side. Forget the term particle. Here's a wall. It's got two gaps in it. And I'm going to fire some tennis balls very, very fast. Maybe I've got some sort of machine that fires tennis balls through the gaps in the wall. And on the other side, there's another wall. This wall here. But just to see where the tennis balls hit the wall, it's been turned around flat, so you can see where they're landing. So you can see where, on average, some of the balls will obviously bounce back. They won't even get through the gaps. It's just randomly firing tennis balls one at a time. So you see what happens here is they fall into two piles, roughly speaking. Of course, none of that sounds too mysterious. I hope that sounds very reasonable to you. I hope you agree that that's what would happen. Let's look at what happens with waves. Now, the simplest way to look at waves is to look at ripples in water. Their waves are different from particles or balls. Waves, if you drop a couple of pebbles into water, they produce a ripple. The important thing is what these ripples do. Here, you can see there's at the top how they overlap, and they produce a sort of pattern like this, almost preserving themselves, but they're overlapping in an interesting way. So what happens if we try and now look at a similar experiment, but instead of using balls, we're going to use waves of water. Just to give you an idea, but first of all, when two ripples join together, they can form a bigger ripple. But if they do, a peak of a ripple joins to the trough of a ripple, they flatten out. So what happens if you send a straight water wave through two gaps, a bit like a ball, the same sort of setup as we had with the ball, but using water. So as it comes through the gaps, as you can see, they produce this sort of pattern, which is the same as dropping a pebble at the point where the gaps are. So they ripple out and they produce this pattern. And as it moves forward, we're going to record where the peak parts are, where they join up to produce a taller wave or a deeper trough, or where it flattens out, and the black parts are where it flattens out. So the pattern you get with a wave looks like this. If you were to think of a wave, obviously a wave is not a bunch of particles, but if you think of it as a bunch of particles, they cluster together a long strip, lots and lots of strips. It's called an interference pattern. So instead of having two piles, you get a whole long strip of interference patterns. So now let's take the next step, and this is the step that's going to lead to the punchline, which is that if we now, instead of using tennis balls, shrink the whole thing down to a microscopic scale so that we're using the tiny particles, which I said before, which could be an atom or any part of it, any tiny object subatomically, let's see what happens. So as you can see in the top left hand there, that's what you'd expect to happen if I was firing tennis balls through those two gaps in the wall. So what actually happens is one by one, if we fire an electron or a tiny particle through, they jump to different positions like this, and they form the same pattern that we had for a water ripple. So looking at it carefully, you're firing a few electrons through at a time, or ideally even one at a time, and you can see they come through the two slits. And instead of forming two piles like you expect, gradually, dot by dot, they replicate the same pattern as the water ripples or waves. They're not behaving as a particle, they're behaving more like a wave. And the thing, this mystery, of course, is that you can do this just by firing one tiny particle through those slits at a time. So what we're now going to do is bring in the final punchline and the biggest mystery of all, and physicists here will know that this is truly the biggest mystery of all. And just as I stand here today, just to inform you, nobody in the whole world understands this. I'll just repeat that. Absolutely nobody in the whole world today, living or previously dead, understands this. Yeah? What is it we're going to see? We're going to now have a look. So we're going to try and trick it. We're going to say, I'm going to look to see where the balls, these tiny particles are going. I'm going to put a little detector here. It's the same as having a look, just look with your eyeball to see. I'm going to try and see which slit has each ball gone through. But when we look, what happens is the electron changes its behavior. The particle behaves differently. It says, I'm going to behave like a ball again. So I'm going to emphasize that over and over again. What we have done here is simply observed it, just taken a look. And what has happened is the particle here, displaying a wave pattern here, has collapsed its behavior down as if it's just a bunch of macroscopic tennis balls. The process by which that occurs is completely mysterious, and there is no explanation.
So in the first one,
Yeah.
the reason why that's just where the particles are landing.
Yes, that's right.
And the second one is observing the path that the particle takes.
Correct, yeah. What we're doing is we're just trying to see, we're not going to detect which slit each, because we can't tell. All we're doing is sending a particle through the slits. We don't know which slit it's going through, because it's so small. We're not going to try and detect it, and it lands on the screen on the other side, and it produces that pattern. The second time, we're actually going to see which slit it's going to go through, And what happens is that the particle decides, I'm not going to let you know really or how I'm behaving, I'm just going to behave like a tennis ball. And the whole point is that its range of possible positions that it could have been has now changed from a whole spectrum of possible locations to just a pile of two possible places. So in other words, the wave-like pattern has changed to a tennis ball type pattern. It's turned into two piles, and those are real pictures. So how do we explain this? As I said to you, there's no explanation. But there is a way that some clever physicists came around, and don't be frightened by this, it's just an equation that actually just talks about something like kinetic energy and potential energy. It tries to give an explanation of that phenomenon. And that's what the whole of quantum mechanics is about. How do we explain this? But the problem is this thing here, this nice looking symbol, psi. No longer do we have any idea about whether a particle has any particular location. We're not talking about the position of the particle. We're not longer talking about the speed of the particle or anything else. We're just talking about this object here. And this object is actually just a probability. That's all it is. So we can no longer describe that phenomenon by classical methods. The only way to get around it is just to say that, well, the probability of it being landing somewhere where it's going to land is higher than it is when the probability of it landing where it's dark. That's all you can say. But remarkably, this particular type of theory is so powerfully predictive on a statistical level that we can actually use it to make very accurate predictions of behaviors statistically on a repeated basis over and over again. It's the most successful theory known to humanity ever created. It's so reliable. Yeah.
It's just to be clear,
Yeah.
so counterintuitive.
Yes, it is. Yeah.
Those two pictures that you showed,
Yep.
the one which the top one there on the right,
Yeah.
on the left, they're the same picture, taken in the same fashion.
Yes, exactly the same fashion.
The second one is not just a picture from this side; it's exactly the same.
Yeah, exactly the same fashion.
Thing that you put in a couple of red lines.
Yeah, you just detected which slit it's going through. That's all. Yeah, and that is the entire central mystery. And the point that you're going to see in a minute, which I'm going to try and emphasize, is that all you've done is you've actually observed it. But the mystery is deeper, which I'll explain in a minute. So here we have this funny thing. So what we can do is think about a little particle, like a gas particle in this room. And we can no longer say, actually, the particle actually is anywhere, really. All we can say is that from that equation, it's somewhere, and it's probably where those blobs are, until we actually measure it. And the point is, it's the measurement that's required to change that particle's behavior. So I'm going to mention that the mystery is going to get deeper. So why do we actually need to measure a position before we realize where something is? The mystery gets deeper, and the point will become clear shortly. I'm going to change it around to something a bit more familiar, because we're used to cats. Well, most of us who've seen cats around or have cats as pets. So now I'm going to talk about cats because we know something very simple about a cat. We know if a cat's behaving normally or if it's dead. Well, hopefully we can tell if it's dead. So that's a very simple macroscopic idea, and this idea was put forward by the same guy who produced that equation, Schrodinger, and that's why it's called Schrodinger's cat. And all we're going to do is you use the cat as a measuring device now. Don't be mystified by it, it's just a measuring device. So I'm going to use, this cat's supposed to be inside a box. The whole thing is one giant box. The box is completely sealed. We don't know anything about what's inside the box, but we're going to use it to measure something about these particles again. So this time I'm going to do a different analogy. So I'm going to give you trying to detect if a particle has something called spin. Don't worry about what that is, because particles have lots of properties. It could be energy, speed, position. But let's talk about spin. Now, spin is nice because the only thing you need to know about spin is that it can be up or down. So I want to know if I send a particle through, just fire it through randomly into this box, I want the box to detect for me whether it's spinning up or spinning down. That's all it can do. No other options, just to spin up or spin down. So how can I use this box? Well, the idea is, the analogy is to show the conundrum and that we face with measuring the object, the properties of the particle. And so we fire it through, and if it's spinning upwards, the cat stays alive. If it spins downwards, the cat's dead. And what happens is poison is released in the box and the cat dies. But the problem is, until I open the box, how can I tell if the cat's dead or alive? And the answer is, you can't until you open it. Obviously, this sounds like common sense, but the point is, that means I don't know which way the particle is, as if I'm using this as a measuring device, until I open the box. You actually need to measure it. Well, of course, you could ask a friend to measure, look inside the box for you, and in that case, whoever looks inside the box first is detecting whether the cat's dead or alive, or in other words, if the particle is spinning upwards or downwards. So what we're doing is we're saying that whilst it's inside the box, the mathematics that we use, believe it or not, and this is an analogy, remember, cats aren't really both dead and alive, but the analogy is that the cat has to be something called a superposition. In other words, that particle that we were looking at, we can never say if it's really spinning upwards or spinning downwards. All we can say is it's some combination of the two. Now, that's completely, utterly counterintuitive. But going back to that double slit thing, the electrode we looked at is considered to be going through, in some senses, both slits at the same time, in a combination of the two until we measure it. And then it becomes either dead or alive, or the particle goes through the left-hand slit or the right-hand slit. And that's the mathematics behind it. Obviously, this is not really what real cats do, but it gives you the analogy that you have to consider them both dead and alive. Heisenberg and Schrodinger have an argument of deciding whether or not it's dead or alive. But here's something I should just say to you, just as an interesting point, that there are current experiments being done right now on a macroscopic level, meaning at a larger level, okay, maybe not as big as cats, but really real experiments that will be showing if larger objects behave this way. And Einstein even was so confused by this, he was so angry about it, that he actually said, is the moon really there when we don't look? So what's happening here is that some observation is needed. And the particles that we talked about in this room, for instance, don't really have a position according to the quantum mechanics. And here on the right was somebody called Niels Bohr, a very famous physicist who contributed a lot to these ideas. And there's Einstein, who was so angry that he actually wrote a very damning paper. He found an argument to trip over the physicists of the time. And this paper is called the EPR paper, after the colleagues he wrote it with, called Einstein, Podolsky, and Rosen. And what he says is that he basically was saying that quantum mechanics was almost nonsense. It was incomplete. It cannot be true. There's a better theory, more complete theory. What he suggested was that there was some hidden information about the particle in this room. It must have a real position. It cannot possibly be just everywhere possible at the same time until we measure it. It cannot be here, there, and everywhere. It has to have a real position and a real speed. So he produced a brilliant paradox, which threw scientists for a while, but actually the argument continued for nearly 30 years. There was no clarity on this, and it was a purely philosophical choice. You either just shut up and calculate, as one view, which is the view of Niels Bohr, what's called the Copenhagen interpretation, or you accept that there's some hidden information that we just haven't found about the particles. If we knew that information, we'd actually know where it really was in this room. Until 29 years later, John Bell. Now, notice the word theorem here, not a theory. This is no longer an idea. This is no longer a guess. This is the theorem. And the difference is the theorem is always true. What he showed is that there is a basic set of criteria which could determine whether or not something was localizable in the room. There were just hidden variables or not. And it was John Bell who actually showed that Einstein was wrong. So in other words, the particle in this room really doesn't have any location or position until we actually measure it, which is completely counterintuitive. Just to give you a very, very, very brief sketch of how we prove this, there's another property of particles which I want to explain, which is related to spin. And here are two particles. There's a pair of particles. One of them can have what's called a spin that's pointing downwards, and the other one can instantly be correlated to have spin upwards. You may have come across this idea. It's called entanglement. But again, don't worry about the technicalities. The point is, this is a phenomenon which can be tested and set up in the laboratory very easily. Likewise, if I measure the first one and it found its spin upwards, the other one's instantaneously downwards. And this is the technique which was used to prove or disprove Einstein's idea. They looked at what would happen if you took the particles very, very far away, and you can do this so far away that there's no light signal or any way of communicating between them. And you can show that if you show that if one of them is spin up, the other one's instantaneously spin down, and vice versa. And there's no way of any hidden information or hidden variables that could be set up to communicate between them, and there's no coding or encryption that could enable us to set this up according to Bell's theorem. In fact, the correlation between them is greater than anything physically that we can actually imagine on a normal basis. In other words, there's something mysterious happening that we don't understand. And the particle there on the left-hand side doesn't know anything about the particle over there. In fact, it has no idea what it's doing. But when we actually measure it, it decides to go up or down. Instantaneously, the other one goes the other way. So, in fact, the reality of the measurement of the particle being up or down, before it's measured, it's neither up or down. It's some blurry combination, a bit like the dead and alive cat. That's reality. Now, this is sounding really a bit very odd. But you see, the point is that we have now essentially a conclusion from Bell's theorem that we're no longer actually locating objects. We're actually almost creating them. These are not my words. These are the words of Schrodinger. By actually observing the position of the particle in this room, we've actually almost generated the particle there ourselves. It's not there beforehand. Now, physicists really despise this idea, and they've tried to fight it off over some years, some decades, and there's no formal solution to this problem other than those which have very bizarre ideas and ontologies. So the idea is that when you observe something, then an outcome occurs. But before that, there is no formal property. There's no dynamical properties of particles or objects. Of course, up till now, this is all about the microscopic level. Things appear differently macroscopically, but that's not because it's not really happening. It's just that other effects occur that blur those effects out and dampen them out. The reality is that's really what's happening. Something called decoherence actually makes it appear this way as we are in this room. Everything looks classical, but it's not really like that. And the real physics of the world is that, not the physics we are used to of tennis balls. So I'm going to move forward. So just to sum up here, you can see that's the position we're left to, which is very perturbing. But there is something interesting about it, and this is where I come into this human beings, finally, I'll skip this one, is that what is needed is our self-awareness, conscious awareness of this measurement. For instance, if I put a machine in the room to measure the position of a particle, that won't help me at all because I have to go and read the machine. So the machine itself, or a measuring device, has to be aware of the outcome. And quantum mechanically, this actually can continue a sort of infinite chain of possible measuring objects until we actually observe it and measure it for real. So really what we need to understand is consciousness. That sounds like a strange leap from physics to humans, but in fact that is the bottom line. We don't understand this. Physicists have tried to blur out the effect, as I said, with other things like decoherence, which is damping, and another solution which I won't mention other than the name, which is many worlds, but they involve very bizarre ideas and ontologies. So we really need to understand from the perspective of my talk here is what is it that makes us aware of the outcome of this measurement. And there we have to look at consciousness. And here we look at what they call qualia, or what makes us aware of anything. Why do we perceive a color or a taste? Or why is it that we are aware of anything at all? That's called the hard problem of consciousness, well, explaining phenomenal experiences. And we don't have any mechanism to date that enables us to do this. So there is the easy problem of consciousness, where we can just locate which parts of the brain, for instance, are active when we're observing things. But we don't have a formal mechanism for dealing with explaining how we experience anything. So we have to then run through a whole lot of ideas that involve computers, brains, information, computability. So we'll start with looking at the brain. Okay, pardon me, again, as I said, I'm going to have to keep it very simple so that as many people as possible can understand. But here we have just the exterior, the shape of the brain, the exterior parts of the brain. You know, the eyeballs are on the right-hand side, the back of the head is on the left. And there you see that you have the frontal lobe, parietal lobe, and very different parts of the brain doing different things. So could it be that if we just look at the brain itself, that we can locate something in the brain that tells us where consciousness is really occurring? And so let's look what happens when we put some light through somebody's eye. Well, the part of the brain that is active is the visual cortex on the right. And here we see that clearly this area perhaps maybe that's explaining why we're aware of it. The answer is we don't really know how we then actually are aware of any visual perception at all, because when the light comes into our eye, the image arrives at the retina upside down, but we never see anything upside down, and something else is going on. We're not even aware of how we turn that into a perception. And a lot of very ideas relating to the activity of the brain occur in terms of when we're conscious, occur when in the front of the brain, the frontal cortex. So this part may be the part that's active. Is that where consciousness is really occurring? Are we just like some sort of machine? Or is it something to do with this area? Now, when we have we see emotional change in a human being, for instance, we have someone who's happy or sad, we see this part of the brain called the limbic system becoming very, very active. And but is that where consciousness is located? And the answer is that if we look at all areas of the brain which are active during conscious perception, there is no one location of the brain which is active at all times. So we can't pin it down. And what this is called neural correlates. There is no one area of the brain which is active at all times. So one step further, what if, going back to that cup of tea, this chap's going to raise his hand, he's going to decide to pick up a cup of tea. We see that there's some electrical activity in the brain before he makes his decision, or even is even aware of the fact he wants to pick up a cup of tea. Now this is where the story starts, because the idea is that are we then somehow as the brain being affected by something outside the brain? And this is the point. The point is that Libet's proposed an idea which was never taken very seriously, called the conscious mental field. And the reason I'm mentioning it is that many of the scientific ideas that follow are actually more like this conscious mental field than anything else that I've come across so far. There's a question of free will, and that's another subject altogether in relation to the Libet experiment. But I'm going to move straight on to this idea and develop it further. And I'm going to say, well, okay, there's a conscious mental field, but before we go on to that, can we just go back to the brain and see, is the brain just a really powerful computer? And does that give us enough information about how the brain works and makes us aware? And the answer is, of course, there's a lot of work being done. You may have come across over the last 20 years approximately, perhaps longer than that. Roger Penrose and Stuart Hameroff, a physicist in Oxford and an American anesthesiologist, who looked at the brain and considered a structure called a microtubule. They're prolific objects throughout the brain, but they have a very interesting structure that enables us to perform quantum computing in the brain. But the way we can do this involves something that will enable these to trigger, like gates and not or gates, so that those things that I talked about before, the collapses occurring of the wave function that we talked about, where we see which, we become consciously aware of it, something has to occur. And Roger Penrose suggested some fluctuations in gravitational fields. Now, notice this. I've mentioned gravitational fields. We don't think of ourselves as gravitational fields. I mean, we don't think of it. Where is gravity? Gravity is everywhere. It's around us. It's outside the brain. So the point is here, we're talking about something outside the brain. This is the essential point I'm coming to, that is affecting something inside the brain, interacting with it. And here, this is one proposal. A much more recent proposal is that funny-looking object there, which looks like lots of billiard balls joined together of different sizes. It's something called a Posner molecule. That's actually brand new information. This is hot off the press, and this is current research right now. Inside the middle of that is something called a phosphorus atom, and the phosphorus atom has this interesting property that its nucleus can spin around, and it can be used to do quantum computing and all sorts of very high-tech computing, which a normal computer can't do. But it has to be protected by a whole load of other atoms around it. That's why it's such a complex-looking structure. So what it's doing is that inside, here's a picture down here of some neurons which are sending signals between each other. What those little blue circles are inside there are these Posner molecules, which I showed you on the previous page. And in the middle of those is the phosphorus atom. And those dotted lines are how they can interconnect with each other to produce a interesting quantum computing that's occurring in the brain. The point is that involving processes that are involving quantum fields outside the brain in order for this to occur, and the computation requires this potentially to then stimulate the brain to then trigger off the release of these neurotransmitters, things that help the brain send signals around it, so to different parts of the brain. So here you see there are other ideas, and I would like to briefly mention them. One of them is what's called the Umezawa and Ricardo's theory, which over the last 20, 30 years, the idea of having a quantum field around the brain that is somehow interacting with certain molecules in the brain. But the clever thing is the information inside the brain, memory information, is actually stored inside the quantum field around the brain, not necessarily inside the neurons. Now, this is a bit of an unusual idea, but it's the idea is that you can actually set up a very, very sophisticated, very reliable mechanism by which memory retrieval and associative memory recall can occur using processes, including quantum mechanics processes, but they involve things that are outside the brain. So here is another sort of artistic representation of things outside the brain affecting the brain. So we're going to move on to, can a brain really be a computer? And the answer is that there are problems. There's something called a Turing-Halting problem, where a computer cannot decide whether a problem will end up infinitely recursive and then just blow up. And there's another problem called the incompleteness problem by Gödel, by which we understand that we see that a computer cannot decide if something's true or false, even if it's true. And that's Gödel's incompleteness theorem. And then most recently, you may have seen in the press, Penrose's chess puzzle, by which a computer won't realize that it can actually solve this problem for whites to win or draw, and then it will end up with an infinite recursive problem, recursive calculation that will just be impossible for the computer to calculate. This is out and available for anyone to challenge right now, and no one has solved it yet. So he said that there are things in the mind, Penrose, that even the most powerful supercomputers cannot actually achieve, and there are quantum effects occurring. And there's one more thing I want to point out: the idea of integrated information, where when we compute things, we have a meal, have a cup of tea, and have a conversation. We blend them together and we integrate them. This is This is a brilliant idea, which has been put together by a neuroscientist and used by mathematicians. It's called integrated information. So the brain is operating in a way that a computer can't operate. And when we do try to apply it to a computer, it doesn't work. So this is the current view of some physicists about the human being. For instance, moving backwards, that Hans Halvorsen at Princeton University has actually written that human beings are more than just bodies, but also living souls. He's taken a bold step, and he shows that it doesn't contradict quantum mechanics. Also, you see Hans Dö, who was a former head of the Max Planck Institute, suggested that we are actually already surrounded by another realm, and that our human body, human self, is actually within sort of a quantum field, which he describes as the spiritual realm. So, briefly moving backwards in time, I'm going to just give you a very short summary of ideas behind what is the soul from the early thinkers. Aristotle's De Anima was the earliest work on this, and he defined the soul as something that exists without the body. Farabi, subsequently an Islamic philosopher, then showed that there was something that was that could be called active intellect. Just to finish off the computing part, then if I didn't have to rush, is that the point is computers can't do what the brain can do. It's as simple as that. And we...
No, there is one thing.
Yes.
I read it, that the computer was made by the human brain. The computer never challenged the brain.
That's right, and that's the conundrum, because the computer can't be conscious. That's the whole point. And because it's made by the human brain, it doesn't have the features. But the main points are the halting problem, Gödel's incompleteness theorem, and the integrated information models. Those are the things. Computers lose information, they break down, and if you try to build a computer that models this, it will come up with unsolvable problems that it cannot actually tackle. So that was the point that I was trying to make, that then therefore we're moving into this new realm where physicists are actually believing that there is something more to us than just the physical body. Biologists tend to avoid talking about this because they don't really understand physics, but that doesn't mean they couldn't understand physics, they just haven't studied it, and it's just another viewpoint. But the reality is that physics gives a more complete picture of us. So I'm going to just compare this to the imagery we have from early thinkers. Aristotle's De Anima was the earliest writing that regarding the soul. Of course, Aristotle was pre-Islamic, but he still mentioned the soul as being that part of the human being that makes them alive. Then subsequent Islamic thinkers like Farabi then defined the soul as something that was quite pure and distinct from the human body, but it had aspects which contain, most importantly, rational thinking and cognition. And he said that the rational soul, the part of the soul that is quite unique to human beings, was the bit that reigns above the rest and carries on living even without the human body. This is the point. So he said that there are other aspects, there is a belief that he had that other beings could have souls. And there is some physics behind this idea that possibly there are aspects of consciousness to different levels that might be present in inanimate objects, certainly biological objects. But the idea is that rational thinking is something that is unique to human beings. Avicenna then subsequently wrote a very encyclopedic work called Ash-Shifa and Healing, and he then proposed that there was an independent, self-conscious, substantial, and immortal soul, and he then posited the separation between the soul and body. And this is the point behind this. And the whole point is that if we now compare the current models of that we are arising from science to what the early Islamic philosophers were thinking, and of course what the Quran suggests, of course, is that of course the soul is distinct from the brain and the body, and that a conscious self is actually contained in something not necessarily physical. So if I then compare it to this picture here, we only language as human beings we know of, because we don't have any other language yet, is that we talk about quantum field. Physicists can talk about that because that's the natural language. It's the most fundamental object there is. It's an object that hasn't got a specific location like a brick. It's a field, and it contains information, or could contain information, that interacts with the human brain and contain even memory storage and retrieval. So you see the similarity is that there's something about something physical which has characteristics that resemble things that we always have believed in as all monotheistic faiths, but most certainly Islam, have believed in, always. So you see that this is a new picture emerging, that there are phenomena outside the brain that actually interact with the brain, and in fact the information that contains self may well actually not be in the brain at all. So here's a more dramatic picture, animated. As you can see, there's a field around it which contains information about memory, conscious thinking, interacting with the physical brain, and producing, using us as a sort of machine. So I just want to point out the word af'ida, and here you see, say Surah Al-Mulk at the bottom is a good example. قُلْ هُوَ الَّذِي أَنْشَأَكُمْ وَجَعَلَ لَكُمُ السَّمْعَ وَالْأَبْصَارَ وَالْأَفْئِدَةَ قَلِيلًا مَا تَشْكُرُونَ. So you see here we're talking about something called, it's been often translated in different ways, but probably the strongest and best way of considering it is this long sentence here, endowed the seat of feeling, understanding, thought, consciousness, intellect, and volition. So this is af'ida. I had a chat with a professor of Arabic in Istanbul in October. I asked him, what does it mean? And he said it was a center of the heart, or of self, thinking and intelligence, the center of qalb that supports the brain, and the biological brain is dependent on af'ida. That he said that an analogy is if the brain is just like a machine, like a computer, then whatever is operating the computer, like you mentioned just now, is the self, is us. So the real I is not the brain, but the af'ida is the center of the qalb, the heart. So I'm just going to conclude nearly now on this very interesting little passage by Paul Davies, which I think is worth mentioning because it shows the fundamental significance of consciousness as arising in the universe. And it just says, what does it mean? What is man that we may be party to such a privilege of being aware? I cannot believe that our existence in this universe is a mere quirk of fate, an accident of history, an incidental blip in the great cosmic drama. Our involvement is too intimate. The physical species Homo may account for nothing, but the existence of mind and some organism on some planet in the universe is surely of fundamental significance. And through conscious beings, the universe has generated self-awareness. This can be no trivial detail, no minor byproduct of mindless, purposeless forces. We are truly meant to be here. And so to sum up, just to conclude, I'm just trying to illustrate to you that a very large number of topics have to be covered in order to understand something like this. But we're seeing that physics and biology and neuroscience and all sorts of things come together, producing a picture of the human that may well be converging to an already pre-existing theological view. In fact, that we may not be just a purely biological object, and our true self may well be captured in something which we can physically describe, in some senses scientifically, but it is very, very similar to our pre-existing belief.